My name is Maha, and I'm very happy to be here. Thanks Dr. McCallum for inviting me and the rest of the organizing committee. I really liked how the theme kind of progressed through the day, and I'm going to rely on a lot of information that you've learned about the source characterization, understanding, validating, and using all the tools at our disposal to improve the simulations. And now I'm going to come at it from the perspective of a structural engineering researcher, looking at what informations can we take from these simulations to inform performance assessment of structures and better improve the representation of hazard in that context. So I'll have to acknowledge that a lot of the work that I'm going to present today primarily started when I was a postdoctoral scholar at the University of Nevada, Reno, working under Dr. David McCallum. The simulations that I'm using were performed by Dr. Arvind Patarka and Dr. Artie Rogers at Lawrence Livermore National Lab, and I did a lot of structural simulations using the Cori machine in the NERSC facility. So there are a lot of reasons why there are challenges with the performance assessment of structures that are particularly closer to the fault than those that are further away. Those are what we call near fault structures, typically defined within 10 to 15 kilometers, depending on the magnitude that the fault is capable of. But generally, two main reasons are the fact that we don't have that many observations for large earthquakes at short distances, and that the closer we are to the fault, the larger the variability. So because of the variability of the shaking intensity, we also get large variability in the structural demands, and because the nonlinear behavior of the structures kicks in, then you have a lot more complexity in assessing that behavior. And so this is why having the simulations for assessing the behavior of near-fault structures can give us a lot of additional information that we don't have. And so in this particular case, a lot of people talked about those simulations today, but I'm looking at simulations that happen at the regional scale, and taking the simulations at the surface of the Earth from the Earth scientists, and then applying them to structures. And then from these simulations, we're able to do a lot of things. And some of the things I'll talk about today include looking at the ways we quantify seismic hazard for engineering applications and trying to identify limitations or improvements to those methods so that we're able to better represent the earthquake hazard in engineering analysis context. And also, I'll touch a little bit upon that last aspect there, where we can actually see from the simulations some characteristics that are lost in the real recordings because of processing of those recordings. And so that's another very interesting aspect of this research for me. One of the aspects that I've really focused on over the past couple of years is looking at what we refer to as the forward rupture directivity effects. As the seismic waves propagate, they accumulate, they intensify. And so we're seeing that structures that are nominally at a similar distance from a rupture can see very different effects due to the fact that the shaking intensity changes as the rupture front progresses. And so those effects have been difficult to characterize and integrate into structural engineering analysis in kind of a robust and coherent way, primarily because we didn't have enough recordings to incorporate those effects systematically. The way this is dealt with in, say, a standard like ASC 7, and I've kind of quoted it here, it's really not specific on how we should incorporate those into the analysis. It does acknowledge that there is a chance we're going to see those types of intense, what we call them pulse ground motions, or they're ground motions with strong velocity pulses in the near fault region, and that we should quantify what's the likelihood of seeing those, and we should incorporate them in our engineering analysis. There are several methods to do that. And I'm not going to talk about them today, but the main takeaway is that those methods are based on small number of recordings, so they have their own uncertainties. In addition, sometimes the majority of those methods, in addition to what we see in the code, it's kind of trying to classify or represent a continuous phenomenon of increasing intensity as kind of a binary on and off kind of classification. So it's either a pulse ground motion that has a strong pulse or a non-pulse ground motion that doesn't, where in reality it's a much more continuous phenomenon and their effect on the structure is the same. So in the typical methods where people look at these ground motions that they call pulse or non-pulse, the probability of encountering that at a location r distance from the fault or the rupture depends on the source to site geometry. This is typically how this probability has been calculated. One thing that it discounts is the site conditions. And using the simulated ground motions, we saw that this can actually have a substantial impact on the way we assess the seismic risk to structures. Specifically, if we have a domain where you have different types of site conditions, in this particular case we do because we're doing the simulation, so we're controlling the site conditions. And I'll add here that these are not site-specific domains that I've worked with, but they're representative of a domain that would have relatively stiff soil, and then part of it will represent kind of a sedimentary basin at the top. So some of it is stiff, some of it is soft, and the idea is that it's sort of representative of a lot of different locations where you would have a shallow basin on top of rock conditions, but not necessarily representative of an actual geology. But the point is, when you don't take into consideration the site conditions, it turns out you may actually discount important effects and not see what you're expecting to see in terms of classifying ground motions as pulse or non-pulse. And so I'll give a little example on that. So in this domain where we have a soft soil at the top there, and then at the bottom where I have rock, this is kind of harder, stiffer soil. We're seeing that if we're looking at kind of mirror stations with everything else being equal and just the difference in the site conditions, we will see that the methods that we typically use to classify or categorize a record as pulse or non-pulse may actually miss the ground motions that have pulse features on soft soils, because those algorithms are typically looking for just kind of one or two cycles of shaking that are predominant in the record. And when you have amplification in soft soils, you end up having multiple cycles of those large pulses. So in reality, that ground motion may be more intense, more damaging to a structure, but it's kind of missed or classified as a non-pulse ground motion. And that's in fact what we see here. So for those two records, the one on the right that is not recognized as a pulse record ends up being much more damaging to this particular structure. And we actually see that, we start to see a pattern of how the effect of the records, as you would expect, is much more tied to their spectral shape, to the shape of their response spectral accelerations, as opposed to this kind of just binary classification that has been typically adopted. And so this kind of nice symmetric classification of what's the probability of seeing those strong pulses around a rupture, and I have here 3 stars because those are different rupture realizations with different locations at the hypocenter. So we don't actually, if we apply the classification algorithms, we don't actually get this nice symmetric shape. We get something that looks like this, that is kind of biased or skewed toward the areas that have stiffer soils. Another way to look at it, if you want to get the ratios of both of them, you'll see that there's a very large likelihood of overestimating the probability of those pulse ground motions in the stiffer soils, and a likelihood of underestimating them on softer soils. And so practically, what that means, just to close the loop on that, that you may be underestimating the risk to structures that are particularly at near fault locations, and that location has soft sediments at the top. So with discounting those kind of amplified multi-cycle pulses, you may not be capturing the whole story. So kind kind of from there also, the simulations enabled me to kind of ask the natural question after that. Okay, so if this approach, if this binary approach doesn't work, do we actually need it? And acknowledging that these types of approaches were developed to compensate for the fact that we don't have enough recordings. Assuming now that we have a large database simulating gram motions and that we're starting to gain more confidence in them, we can use them to supplement the recordings in near fault locations. Do we still need to do this classification? And people have studied this in the past. They've looked at structural domains as a function of ground motion intensity, and to understand or quantify statistically the role of this pulse classification, you would typically kind of look at structural domains as a function of both a ground motion intensity measure, in this case, spectral acceleration at a particular period, and then the pulse classification as an additional variable. And then you try to statistically see if the trends are different for each type of ground motion. And well, they actually are, but only when you look at it, when you realize that you're only looking at one single measure of the ground motions, that is just a spectral acceleration at one particular period, which we all know now is not sufficient to classify or to understand the damage potential of the entire record. And so we had to be a little smarter about how we study this relationship by looking at the spectral accelerations at multiple periods, or a larger portion of the spectral shape when we compare different ground motions. So in this case, we did something similar to this, I'll call it one-dimensional regression, but we did it in kind of a non-parametric regression fashion, so that we're able to see whether or not the pulse classification matters when you're actually looking at the full spectral shape, or at least a substantial portion of the spectral shape, and its effect, its influence on the structural demands in buildings. And you'll have to take my word for it, because I'm not going to go over the details, but you can go to the paper and look at the details, and it turns out when you actually look at the full spectral shape, as you expect, the pulse classification doesn't actually matter for those particular experiments that we conducted. And you see that from the very large p-values that we're seeing here on the right for different types of, different heights of buildings. And again, practically what that means is, if you are looking at selecting representative ground motions that match a particular target response spectra, like what I have here, and those spectra are highly dominated by very strong pulses and from a very near fault location. In this case, we also know what the target risk is, because our target hazard spectra are based on simulated ground motions. And then we go and select a bunch of records without looking at their classification. We don't care if they're pulse or non-pulse. And then we go back and select records that are specifically pulse. And then we try to see, will they lead to different impacts on the structure? And the answer was, they're very statistically similar. So this is good news, because a lot of the methods we use today to select ground motions rely on selecting the full spectral shape. So if we're already doing that, and we have enough simulations to match the spectral shapes that we need, then we may not need to do this classification altogether. And I'll want to point out that the simulations have been helpful in this particular context, not only in providing a large database to select from, but actually I've done some work to show that they can be helpful in determining what the target hazard is for some near fault locations. But that's another story, and another paper that will be coming out hopefully in the next couple of months. Now, I'll quickly jump to another very interesting topic that I've studied recently. And this is looking at what we call fling pulses that appear in the fault parallel component of simulated strike-slip earthquakes. And this is kind of I'll call it a spin-off project that I've worked on over the past year. It was funded by USGS, and I worked on it with Exponent. And the simulations were run also by Dr. Arben Patarka. And the structural simulations in this case were run using the Texas Advanced Computing Center, the Frontier machine. But what I mean by fling pulses is that using those same simulations, we're able to see this effect of the kind of sudden permanent offset in the ground displacement. And that happens very close to the fault, for locations that are very close to the fault, and especially for very shallow ruptures or ruptures that burst to the surface. And like I mentioned, for the strike slip earthquakes, we see that predominantly in the fault parallel components. So it's completely separate from the rupture directivity effects that we see predominantly in the fault normal components. But nonetheless, we wanted to take a similar approach to see whether these pulses are important for structural demands. And the trick here is that those fling pulses are very difficult to obtain from the chordate ground motions. Actually, most records are processed to eliminate this kind of permanent offset in the ground displacement records. So we can't really see those displacements in recorded ground motions, but they are inherently incorporated in the simulations, and we don't need to do any processing for the simulations, and that's why the simulations present a very valuable tool to studying these types of pulses. So I think the results that we're seeing are very promising. So we used the rupture simulations that we have. We looked at the permanent offsets in those simulations. We compared them to a group of recorded motions that have been especially processed to preserve that offset. We also compared them to some empirical models that have been developed to predict that permanent offset in kind of an empirical, similar way to empirical ground motions for predicting other shaking intensity measures. And so these simulations have shown that the permanent offset that is predicted can provide us with somewhat reasonable answers to some of the questions that we have regarding their effect on the structural response. And that's kind of what I'm working on at the moment. For example, I'll give a quick example. We see that ground motions with strong fling pulses actually tend to have larger spectral accelerations. So we have different spectral shapes than those without. And so on the left here, you're seeing spectra for magnitude 7, distance of 1 kilometer for one single rupture realization. And we're distinguishing between records that have permanent offset over 0.5 meter and those that have less than 0.5 meter. So we're seeing a large difference in their spectral shapes. And then it's also an interesting question to think about what properties of the rupture lead to those differences. Because in another rupture realization on the right, we're seeing also kind of a difference in the shape. However, the difference is kind of limited to periods that are relatively long, longer than about 1 second, whereas the kind of higher frequencies are kind of the same. And so all of these differences will have substantial impacts on the structures, and it's also important, it's important not only to connect them with the structure's impact, but to connect them with the causes in the simulations as well, so that we're aware of what parameters in the simulations change substantially the properties of the shaking characteristics and then lead to propagate into substantial impacts on the structural demands as well. So with that, I will summarize what I talked about today. So primarily using the earthquake simulations to better understand the seismic hazard quantification and improve the way we represent it in engineering analysis. It's not just a matter of adding a large database, although that's very helpful, but also I think for my research it's been very useful to use these kind of carefully designed and conducted numerical experiments of simulations where we're controlling the rupture realizations and the characteristics of a rupture in a way that we will never be able to for real records. And so getting all of these phenomena that can have very substantial impacts on the structural behavior, and then connecting them with both their causes in terms of the rupture characteristics and their effects on the structure so that we're better able to improve the representation in engineering analysis. With that, I will close, and feel free to reach out to me if you have any questions or if you want to chat about any of this. There's also a QR code if you want to go and look at some of the publications on the stuff. Thank you very much.